Howdy folks, how you doing today? Happy Thursday. Alrighty. Sorry to miss you in person again. I've got this is lingering cough now. I think mostly better. Still don't feel great, but definitely not as bad as it's been. So I think next week I'll be back for sure. Although we have midterm week, so no, nothing next week. That's right. So that's okay. So we're going to finish up talking about linked lists today. The lab for linked lists then will be on 3/8. So that way you've got time in lab and lecture time to do work on this midterm for that, if that sounds all right. And then we're going to tackle, we're not going to finish all of the chapter on linked lists today. We're going to leave the last little bit kind of as an exercise for lab to build out the last little bit. We'll talk about that in a little while. And then we can move on to trees. We'll spend a decent amount of time on trees, priority queues, maps for sure. Hash tables are fantastic. Skip lists we don't do a whole lot on. Search trees we'll do some basics. We're not going to do all of them. Some basic sorting and selection, and then a little quick lecture on ethics, which is super important. I'm glad we're incorporating it into the course for sure. And then time to work on that final project. The last week of class, you're looking out to April already, more time for the final projects, and then presentations 428 for our final projects. I didn't realize this was the Thursday because I had it penciled in wrongly before. So I've got a conflict like right at 3. I'm hoping we could probably like start at 4 because I have to go to my specialist's office, and like they're booking 2 months out for appointments and things if I cancel. So hopefully we can start like 4 if you don't mind on Thursday, and then that'll go pretty well. But I'll let you know again ahead of time when we get there. Yeah, we're coming up pretty quick on this. So we have the project due today, our little maze solver. So we'll go over that first, and then we'll come back to linked lists. And then we can go from there, if that sounds all right. All right, so let me go pull up our assignment here. I did get some of the Trek Wars projects graded. I've not got them all done yet, I'm sorry. I'll be working on those and the project one over the weekend. Get those in for you before you do the midterm. Apologies for the delay. Grab this one here, we'll PyCharm load up. So something like this for a little maze here where, you know, spaces, walls, start, end, that sort of thing. We can find our way around. I thought I was loading PyCharm. Oh, excuse me, sorry, I forgot the mute button there. I need like a keyboard button for mute, that's what I need, a little shortcut. And then we have to figure out, again, the shortest possible path. So we'll start with how we can just solve any method here, or any maze here, and then we'll look at doing the shortest possible path, and then we'll work on some unit tests for it. I'm trying a couple different interesting scenarios. Let's see. All right, there we go. We're getting there. Maybe. No, come on, flip over. Not that one. I keep stuff in like in a scratch file here. PyCharm's fun for that. Come on. No, thanks for the tips. Actually, that one looked kind of interesting. That's okay. New project. Maybe. There we go. Here's project 1, the maze solver. Oh, excuse me. Oh. I tell you, the cold meds are good though. They do make you feel better, but sometimes you're feeling better because you're so loopy you don't really know what's going on. All right, so we wanted to write our maze solver class here. So we'll write a class for maze solver. And oh, we zoom that in a little bit here. And then again, we had this init idea here that would take an argument for the maze. So if you give me a maze, I will go solve it for you. Why is it not lighting up purple? Maybe that's loading here. I want it to light up purple. There it goes. Okay. All right, so we're going to have our self maze as the maze you give me. Great. Then we need to go find the starting location. Right, we need to know where we're going to start here. So we'll say for row in maze, right? Because this should be like a two-dimensional sort of list here. We can then find the start location, but not all of it's going to have it here. So we might as well just loop through for space in row. If space is equal to s, then we know where our start is here. But we need the row and the column. So probably better off then, right? We need columns and rows, so we need the indexes here. So let's make this row index in the range of the length of maze. And let's do this the column index, right? Because I can't just find the value here. I need the row and index number. So for column index in the range of the length of self.maze at the row index. Now this does seem a little silly here to be that specific, but what that's going to let us do here is my maze now doesn't have to be a square, right? If I'm going off the length of the row. Right? Nothing says it has to be a square. So this gives me the flexibility here of being a possibly rectangle, or even each row might be different than the next row. You could have some sort of like a jagged maze here that we'll look at for some of our edge cases, which are kind of fun. So then we'll say if the self maze at the row index at the column index is equal to start, then right now I've got my starting location here. And really, I can just go solve from here, right? We'll call self.solve, given the row index and the column index. Great. The other thing we're going to need is a couple other variables here. So we'll have the number of current steps, right? And then I saw a couple people had, they kept a list of solutions. That's fine. I'm going to do it the harder way, I guess. And this is the self.shortest path. You know what? We'll do that. So this is self. This will be the solution steps per solution or something per solution equals a list, and we can start adding when we find a solution the number of steps it took for that solution. I like that, and then we can just give them the minimum value here. That worked out pretty well, because then you don't have to worry about if you had one or you didn't have one. Probably okay. Okay, so then we'll go solve here. So then to solve, define our solve method. Given self, we need a row index and a column index. Okay, so when we were looking at solving a maze, we said, hey, we need to do a couple things. We need to see, can we go up? Can we go down? Can we go left? And can we go right? Right, those couple operations here. So we need to know if we can go somewhere, then we'll go that place, right? So the first move then, right, every time we call solve, we're going to try and take a step. So I think starting at start here is no steps. So I'm going to say, hey, like, if can, how about self that can move to a row index, column index. Now we want to do a couple here. So let's say this is up. So row index would be -1 to go up. So if we can move to up, then we'll do the move up thing. So to move up, then we're going to mark, we'll go call solve right at that location. Or, you know, we kind of want to leave that breadcrumb trail here, but I don't like overwriting the S here. Not the biggest fan of that here. I don't know, maybe it's okay, maybe it's not. Hey, thanks for following along. So how about we say, if my self.maze at the row index at the column index, oops, sure, does not equal an S, then we'll set it equal to, how about like an X here. Right, we'll say, okay, or not an X, maybe, yeah, we can do an X. That's our little breadcrumb. Okay, so we're marking that we stepped somewhere. Sure. So for not at the start, and probably also not at the end either, right? Because you don't want to overwrite the end. And it's not an end. If it's not start and it's not end, or it's not end, if it is start, that would be false, and ending together is proper here, right? This should be fine. We'll mark it with an X. So this is actually step somewhere except on S and E spaces. Oh, I cut that whole thing out. I didn't want to cut it out. I just wanted to mark it. There we go. Okay, so we'll set that here. We'll say, okay, we want to go somewhere, right? Then we need to count it as a step, right? So let's mark our breadcrumb, and then we'll take our Well, I think actually we said we're going to count it here. That seems a little bit redundant, though. It's kind of annoying. Um, how about this? Let's see. So, right, we have with recursion, we have either we're done, we reached our base case, or we have more to do. So we shouldn't be able to move to a wall because of our can move to. This should keep us from trying to move onto a wall space, I think was the idea here. This is, if we can go up if there's no wall there or it's within bounds of the maze. So this is only saying, because start and end are like valid places where solve should happen. But this one is our solution here. So we can say, if our maze, this is our base case, solved. If we are solved, then we'll take our self.steps per solution and we'll append the self.steps current steps. Oh, I should probably set that to something, right? Current steps, there we go. Why 2? There we go. So we'll take our current steps here, but that's it, and we're done. So we can just return. Right, that will stop this from going any further. We could put the rest of this in an else if we wanted. That's fine. So I guess now then, if this is if we are in E here. Let's do this. So we don't even need to check if we're not in E, because this won't happen if we are in E here. We're just going to return. We'll add our steps here. So every time we call solve, let's take our current steps, self.current steps plus 1. Right? So starting with 1 step, because we're going to not count moving to E here. Or does that count moving to E? Maybe that counts moving to E. We'll see how well this works for us. We might need to adjust this later. Okay? So if we can move up, then, right, we marked a breadcrumb. We're going to move up. So let's try moving up. So we'll call self.solve at row index -1, column index. We'll recurse. When we come back, when this function call is done, right, as many as we're stacking up on the call stack, whether or not we find a solution or we hit a dead end or whatever happens, when we're done here, we need to undo the marking step here. Right, put it back to a space. Right, with this recursive call. Put it back to a space, and then we're going to take our current steps down by 1, because we're undoing here. Down by 1. Right, and essentially this is the same operation here then. So we're going to check, hey, if we can go, tab in, if we can go down, right, that's row index +1, +1, right, and if this is all the same operation here, right, I feel like this should probably be a method, right, or another function, right? We don't want to have to repeat ourselves over and over and over. That's going to be no fun here, right? So let's change this then, and we'll define a how about a try move given a row and column, row index and column index, row index and a column index. Okay, and to do that, we'll say if we can move to that row index. Great, let's move to that row index here. When that one comes back, we will undo right, and take away the step. Is that going to do what we want? I think that's going to do what we want. No, it's not going to undo the mark, though. We'll see. Maybe it will. We'll try it. So we can just try self.try move to go row index -1, column index. Right, that's up. And then we'll try down. We'll try and move down a row, row +1. All right, let's space those out. And then we'll try, how about left? And then we'll try right. So to go left then is going to be column -1. And to go right is going to be column +1. Right, after we've tried all of those, Do we need to mark it here? Maybe we can undo it here. I think we'll undo our breadcrumb here. Let's try it here. We'll just undo our step here. I'm getting myself confused here, folks. I'm sorry. Still got that brain fog. Because we marked it here. We need to undo the mark here. Yeah, we don't want to. Yeah, we don't want to do it here. This is if we can do. Let's do that. Is that going to work? Maybe it'll work. And then we will reset our space, right? Because we just put an X here. I guess if it's not an S, we could probably check that again. Because we don't put an S there. And then take the steps down by 1. So we don't know if this can move to yet. We have to do this one still, right? How do we know if we can move somewhere? Well, let's define the can move to. So we can move to a row index and column index if a couple things are true, right? First, the row index needs to be between 0 and the length of self.maze, right? There has to be a valid row there, but less than the length, right? And the column index has to be valid, which is 0 is less than or equal to the column index. And now, because we want to deal with rectangles or possibly even the jagged rows, we need the length of self.maze at the row index. Nope, row index. Oh my goodness. Row index. Oh, less than, that's why. It's missing that other symbol. So less than the length of that, right? And then what else needs to be true? Well, we can move there if it's open, right? So my self maze at the row index, column index is open, right? Or it is the end, right? We definitely want to be able to move on to the end here. And because we're ORing this, I need to make sure I force some order of operations here. Oh, I missed my... And nope, that wasn't it. I think I just need that slash. Let's tell Python, yes, this is supposed to go down another line here. Now we'll kind of tap it in. Right, so if the row index is valid and the column index is valid and it's a space or the end, I can move there, right? Because I need to call solve on this end space to say, yes, I found a solution. Okay, so we'll see, we'll try and move there if we can. If we can move there, we'll move there, right? This just saves a little bit of typing here, right? Because it's a two-step thing. And when we're done, let's try and undo. I think we're going to need to undo in try move. We are going to need to undo it here. That's a bummer. Maybe not. Let's try it and see. We'll try it and see. And then we should define that string representation, so we can just like print ourselves here. We did one like this before for chess or something. That one. I don't have to middle here. Oh, it says my encoder is overloaded. Oh shoot, did I mess up my settings again? I haven't seen that in a while. Let me see what happened here. I'm checking my OBS settings while we do this. I think that was in what? No, it's using the hardware encoding, so maybe I just a poor computer. Yeah, here's this little string representation. And look, I'm even going to cite my source here. So I can pick right here, pick that line, say from here, sure. We'll return that result. And now not self-board, this is self-maze, right? Turn the row into a string, return the result. Okay, now we need that minimum number of solutions, right? And actually, I do want to see, I want to print myself here. If we find the end, I want to print it here and see if we like what it looks like when we found the end here. And we'll define a shortest path given self is going to return the minimum of my self.steps per solution. So every time I find a solution, I'm going to append the number of steps, right? And then we'll find out which one was the smallest. We can use that built-in min function. So let's try it and see. Let's give it a little maze here from, like, we do the sample one here. So here's a maze. We'll make a maze solver. Solver equals a maze solver given the maze, and then we'll print solver.shortest path. Give that a run. It might not work. It probably won't work this first time, right? Probably going to have some errors. Let's see. Oh, goodness. Did it work? Oh, yeah. Okay, so I found one solution here. I'm really amazed that it worked. I really thought I'd have some trouble here. Here's another solution that worked, and here's another solution that worked. Minimum number of steps here was 10. Does that look right? So 1, 2, 3, 4, 5, 6, 7, 8. Uh-oh. We're miscounting a couple things. I think that's probably because we're counting the start as a step. So it should be like 1, 2, 3, 4, 5, 6, 7, 8 here. And we're also counting the end. So how about we say, let's do this if it's not in S. We count the step. And we were not counting start, and we're not going to count the end either. So we don't want to count that last one, or double count the last one. Let's see if that works any better for us. Let's give that a run. Oh, now we have 7. Okay, now it's not enough. Uh-oh. Looking better, but not enough now. Okay, so maybe we just do it. Can I just do it here? Maybe? Let's see. 8. Okay. So why was it not? Oh, because we weren't counting end, we have to count start. But we don't want to count the end. I think that sounds right. So this is counter steps then, but it's not going to count when we reach the end. So because we're going to count start as a step, so this is technically 1, 2, 3, 4, 5, 6, 7, 8. And then we get to end, it doesn't count the 8th step or a 9th step because we counted, really starting here was a step. So I think that's working okay so far. Right, that's actually really promising. So the base case is solved, and this is essentially base case reached a dead end from the recursion. Right, the try move was the recursive part here, and we reached the dead end. We came back. This method call finished, so now we're going to undo those steps here. Okay, so we should give it a run. So 8 was the shortest. Cool. Can we mess with this here then, right? So let's see, if we put it like over here, we should get 1, 2, 3, 4. Right? But there'll be a couple other solutions again. Should get 4. 4 is looking good. What if we put it over here? Right? 2. Okay. Looking good so far. So what if we did some silly things and like added another space here? And added another space here. Added a start right here. So that should be 1, 2, 3, 4 steps. This should still work, right? Because we're being flexible with our rows and columns. It can't go up, it can't go down. They're not within range, but it can go left and can go left. And then it can do anything else it wants to do here. Right? Okay, that's maybe a little bit contrived here, but if we put this back. Now, you'll notice if we do some other silly things here, like take out all the walls. Here. Take out all the walls, and we'll just put start. We put start here, and what if we put the end here? There's going to be a lot of possible paths here for it to take. This is going to take a little while. I mean, it wasn't too bad here, but okay, sure, 1 step. Because it has to try every single possibility. So from here, which way can it go? All right, from here and then here, which way can it go? From here and then here, which way can it go? So it's going to do a lot of this backtracking here. So the more open your maze is, the slower it's going to be, which is okay. You know, not the worst thing in the world. But you'll notice it's not going to work very well for large mazes. Where do we want to put our start? We'll put our start back up here. But we could try larger mazes, right? We could make more interesting ones. So for the unit test, the idea was, if I know what the shortest path is and I know there's longer ones, is it working? And then we want to try and make sure, hey, it will work for other locations of start, essentially. Right? That sound okay? So how'd you folks do with the maze solver? Again, the key part of it here was the undoing. So it was leaving the breadcrumbs here. And if you overwrote start, it really doesn't matter. I'm not concerned if you put a mark on S or not. Well, so minimum number of steps is the shortest solution. Right? It was calculates the shortest possible path. So what was the number of steps? Are you saying like the entire solved version of the maze? We could do that too, pretty easily actually. So we could have then, well, let's do this as a dictionary here. And when we find a solution, let's add in here. Yeah, we could do the whole maze, sure. We'll add in here then key of the self-current steps. And the value we're going to associate with that then is going to be the string of self. Right, let's turn our self into a string here. Save that with the value associated with the steps here, and then to get the minimum shortest path here, we're going to find then, we want the keys. So we need the minimum of the self dot steps per solution dot keys, right? And we want to then return the self dot steps per solution index of, or a key value associated with that key. So get the shortest possible number out of that dictionary here. For every possible solution, find the minimum one here. Oh, I missed min here. Sorry, min. Minimum here. Give that as the key in that dictionary and get the associated value back out. So now when we print it here, we see it was 8 steps. We can also have we string. Maybe we add in here current steps. Right, result plus equals self dot current steps plus number of steps, or steps. I don't know. Sure. How about just 8 steps? Here, and actually, I want to do this as a formatted string because I like those so much better. So do that as an F string. That's so much prettier. Right. We'll add in here. Okay, this many steps. Right, and then another new line, right? Okay, now we give that a run, and we'll see, it tells us how many steps it was. 8 steps. Oh, we got too many new lines, shoot. I don't need that new line there. There we go. So that was 8 steps for the shortest possible path, and now we have the path here. So you can take advantage of this string result, string of self here, and we could just store that string result in a dictionary then with those other values. Right, so we wanted to make this bigger. Let's see, can we take, let's do like a bunch more of these maybe? So get out the start here. Okay, so let's add a bunch more walls or something, right? Right, and then let's move that end character, and then let's take a bunch more of these rows. Let's see what we want to do over here. And maybe we'll put the end over here just for fun, right? Space, and then throw some walls over this way. Right, we could do some fun options. I'm not a very good maze builder here, right? So we could have some different paths here if we wanted. Sure, why not? Maybe put a wall up here, one up over here. Oh, not there, but what if we had one like over here and over here and over here? I don't know, sure. Like this, some sort of silly maze looking thing here. Are we lined up right? Something's not lined up right. This one here needs a space. Okay, there we go. That looks a little better. So let's try solving that one, right? So it should be, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 steps, I think. This is the shortest. This is what I can eyeball. We get 21 steps. Look at that. Hey, that was the path I took. All right, I know I just built it myself, but I feel like I'm kind of proud that I get the shortest path possible there. Yes, we can do it either way, Trumpet Man. Definitely. Whichever way makes sense. So actually, this would then would get us a shorter path, right? If we don't have to go up and around. Now we should be able to get is that 3 less steps here. So let's put us at 18, I think. Hector, thank you so much for donating those bits to the Student Scholarship Fund at the University of Michigan Dearborn College of Engineering and Computer Science. You, sir, are quite the friend of the channel. We appreciate you here. And hopefully, I don't know if you heard or not yet, we actually just got a payout. I don't know why I say we. I just got a payout from Twitch, about $125 or so. It's in the About Me section of my Twitch page here. That brings our total donations now up to the Student Scholarship Fund to $250, simply because I've been using Twitch and of generous friends like you. So thank you so much for that support. I know it's not a ton of money, but like that's money that wouldn't have been there otherwise. So that's super cool. We can get that Student Scholarship Fund moving here. And I'm happy to show you receipts anytime as such a generous supporter of the channel. So thank you, my friend. Appreciate it. Okay, so 17 steps this way then, right? If we can avoid this little loop-de-loo this way. Yeah, so Chloe, the dictionary then will only accept, or really because it's an add or update, the last solution with the shortest number of steps. So if there's more than one solution with 17 steps, we'll get the last version with 17 steps. Yeah, because it's only ever going to have a single key at a time. So if the key is our number of steps, then we can only ever have one solution with that number of steps, which I think is fine. I don't think that's a big deal one way or the other. But now for fun, like if you really wanted to go see it here, we could print here our solver. And now we're not supposed to do this, right? But you know we can because Python's trusty. We can go print this dictionary out. What is that? Steps per solution. Solver dot. Oops. Oh goodness. What do they do here? What do they do? Solver dot steps per solution. We can print the dictionary here, and we'll see what it looks like. Okay, that's not pretty here. Ooh, that's interesting. It has new lines, but it didn't actually like record them as new lines. Oh, because they're inside the dictionary. I think is probably why. We see there's a couple different solutions here. So how about, okay, we'll do this. We'll say for, how about, we'll just say solution in my solver dot steps per solution. Sorry, that's a bad copy paste. Dot values. So I want the values here. We'll print the solution. Solver. Here. We can see all the possible solutions here this way, right? Not necessarily just the shortest one. So shortest was 17, so we had a 33-step solution here. Oh man, like I used all of those. We had a 29-step solution this way that went up, down, and around here. That's kind of funny. We had a 35-step solution here. We had a 31-step solution here. We had a 37-step solution here. We had a 27-step solution. 25, 23, 21, 19, 17, 41, 39, 43, 45. So 45, I think, is the worst possible solution that we could find here then. Sorry, I should zoom those in a little bit here. Well, so like ideally the maze solver init method accepted the 2D list for a maze. That was here in the rubric here, Trumpet Man. I'm sorry if that wasn't called out. It's like I gave you here's an example maze. If they make their own maze in the program, man, that's intense there. I apologize you went and did all that work. That sounds awful. Wow. But cool that you can build your own maze, I guess. I mean, that's pretty fun. Right, so the solver should just, here's a maze solver. You go solve it. And not all mazes are going to have solutions, right? So if we go and mess this up here, right, if we just put a wall here at start and we try and run this one here, we get, min arg is an empty sequence. Well, there were no solutions here. Oh no, 200 lines of code. So probably a better thing to do here then, right? If we know that there's a value error, right, we should handle that. We should deal with it here. So when I get this, we're going to say try this thing here, and then we can accept a value error as E, and then we can just return something like no solutions found. right? And now we'll get something nicer and we won't crash. We'll just say no solutions found, because we know that this possibly could be a value error here. Yeah, the solver was only 60. Oh man, yeah, what did we end up here in our solver? So we're at 63. That's not too bad for our solver here. I think that's reasonable. With a little bit of some, okay, a couple extra notes here, but that should be fine. Try up, try down, right? This could be optimized. We could do a loop here, like we did kind of for that Knights 2, where we had all the possible moves. We could have some sort of tuple or something like that, or tuple of tuples that they could iterate over for each possible move. They could try that. I think this is not too obnoxious, up, down, left, right here. With the Knights 2, it might have been a little trickier to have 8 of those, but either way should be fine. Okay, and then this try move just saved us like 2 lines for every 1 line we called it here. Not super interesting. But I think that works then, right? Feeling good about this? Now, the next fun thing you can do, which is a little harder on the brain, if you wanted, and I'm only putting this out here as, if you're bored, I've seen people do a 3D maze solver, where you imagine you have rows and columns, right, in this 2D flat grid, and then you stack them on top of each other here. So I could say, okay, could I go up a level in the maze to another 2D grid here? So like this would be level 0, and then could you climb up a level to level 1 and have another 2D maze, and climb up a level to another 2D maze? Now displaying those are super painful, and I just hurts my head. And generally, I'm going to be of the mind that after 2 dimensions, you probably could do something better with a class anyway. But it's not the craziest thing in the world to try and imagine a 3D maze solver that can go up, down, left, right in your 2-dimensional plane, and then you could go up a level or down a level to the next 2-dimensional plane. And those are a lot of fun to do too. Oh, we got an extra comma there. I should get rid of that. All right, so let's pull up GitHub here. I've had a lot of coffee today. I'm trying real hard because it's really gotta keep myself hyped for this. Hello, Fish. Good to see you, my friend. I haven't seen you in a while. Hope you're doing well. Friends of first extending with diagonal diagonal steps. Ooh, that would be fun. So could you go like +1, +1, or -1, -1, or okay, I could see that. That's not what I wanted here. I wanted 2001. Go to this one here. It's debugging someone's code. So would you count a diagonal step as a single step then, Blowfish? Right, is that still just 1 step? Because technically you're going further of a distance, right, to go diagonally. Here's our maze solver. Here we'll commit and push that. I'm going to talk a little bit more about linked lists. We'll save the craziest part for lab. It always makes for a fun lab. But right, before we move on, are we okay with our maze solver? This makes sense what we were trying to accomplish here. So backtracking recursion was the 4 points, 2 points for being able to calculate the shortest one. So if you were only able to solve it and not finding the shortest one, you still get most of the points here. But then points for figuring out which one was actually the shortest one, and then points for testing it. Again, just making sure we could go in. So I should do a test. I apologize. Let me go do that before I forget here, because that's good practice. We're going to say go to test. And we're going to make a test for shortest path. All the other ones are private. We don't really care. And like solve kind of automatically happens already, which is interesting. So maybe that could have been even been a private method, private function. Not too concerned. So let's go give it a maze here. So we'll say, okay, sure, here is maze. We'll take it out of this one here. And really, like, all of this probably shouldn't even be in here, right? Or we could hide that with, like, the if name is main here. If name equals main, right? I think that's what it was. Main. I always have to go look this one up. I think that's what it is here. Sometimes I forget. But we'll copy this maze here. Right, we'll do all the same stuff here. So we're going to arrange. We'll make a maze. We will act by making the solver here, and then we'll have an actual shortest path is, we want the shortest path here, right? And now shortest path was still just the ooh, that was printing out the smallest possible solution. Oh goodness, that's going to be a small pain here. I don't actually want to test that one. We got to import our maze solver too. So from main, right? Because that was our main. We just called it main.py. We'll import maze solver here. So the actual shortest path is the shortest path, and then we'll also have in here an expected shortest path is equal something. Sure. Well, let's give this one a run here. Oops. Let me comment this one out here. Just want the shortest path. Why is it not like solver now? Oh, that was indented wrong. Can I do it now? There we go. I'm going to see if I can do this here. Let's try this here. Now it's ugly, but I think it'll work. So in our test here then, our shortest path will equal, you can do this cool raw string, and you can give it this 3 lines, but not the process ended. So remember, a raw string gets like, everything here is just going to be treated as a string until it sees another triple quote. So I think this will do it here when we assert then. Self.assert equal the expected shortest path and the actual shortest path. Shorted path? Shortest path? There we go. Let's give that a try. Just trying to do this in a quote is going to be really ugly. I think the triple quote might work for us. Oh no, it failed. Bummer. What did it say? What did it say? Does not equal... where is it different here? I think that was the shortest one, right? Okay, that's all right. That's all right. Let's put a break right here, and we'll debug our tests. So the other cool thing is you can debug unit tests. Right, so you can actually see the values here. Let's see what the two of them look like before we actually run that assert. Yeah, maybe the line break. That's probably what it is. So here's our expected shortest path, and here's our actual shortest path. So there should be, where's my option? I can inspect. No, inspect is awful there. Oh, view, the view. Here we go, here's the view. So there's a new line here at the end of shortest steps. You can see there's one last new line here. But when I view my expected shortest path, there's not a new line. So I was wrong with moving up that triple quote. Okay, let's try it one more time. Now we'll see if we can run our test. All right, and now it passes. Hooray! All right, we feel pretty good here. Do you feel good now? Does this feel good? Hopefully. Oh, excuse me. Actually, can I bump that down one? I hate the formatting on these. That's fine. Cool. All right, so we'll commit this here with an added test. Whew. And we'd already done like some of those where start is not in the top left, end is not in the top right. So that would have been nice to include in the test here, but I don't want to have to redo all of this work. That sounds really obnoxious. I guess I could like move start to here, move end to here, or something silly. But so the idea wasn't 100% code coverage on these tests here. It was just, can we actually get the correct shortest path here, right? Where if I know there's longer paths, is it properly calculating the shortest one? Just like what we did here in main, but without having to eyeball it. Right? We shouldn't have to rely on a human to say, oh yeah, that looks right. Right? We can go and actually put it into our code and have some fun with it there. Okay? All right, cool. So let me close that one out, and let's open up now our linked lists. So we'll finally actually get something that looks like a list here with linked lists. Okay? So we ended up with our last iteration here was the circular doubly linked list deck, where you could add to the front, you could add to the back, you could do all sorts of fun things. Okay, so we're going to take this version here then. We're going to go change it. Now let's call this a circular doubly linked list. So it's no longer a deck. So we don't want the deck operations of limiting us to adding to the front, adding to the back, taking from the front, taking from the back. Right? We want to get rid of those. We want to do better. Okay, and we can do better. So if we want to do all of the list operations here, then adding to the back is append. Right? That adds to the back of the list here is with append. Right? There is no add to front. Right? But what we get here now is an insert. We get an insert, and now we're not sure what the O of this performance is yet. Right? We'll find out what that is after. Right? So to insert, you tell me what index you want to insert to and what data. Right? And now we don't have a front, we don't have a back either. We don't do these. And we don't have a remove front, we don't have a remove back. We don't have those operations. Okay, we'll get to the other operations here. So if you insert at a given index, well, first we should make sure, is the index valid? Right? So if the index, I don't know, if 0 is less than or equal to index is less than the length of self, then we're good. Right? We'll go do something here. Right? If it's not, else we'll throw or raise a index error. Right? Raise an index error. Okay, so if you give me a valid index, we'll go insert ourselves. So how do we insert ourselves at a valid index? Well, I need to put myself in between what used to be there, or I need to put myself where that used to be. That will now come after me, and whatever came before it comes before me. So I need to go find where that index is. So I'm going to say current index is 0, and then the current node is the self.start.next, right? The first node. That's my current node, right? And again, you can't insert when there's 0. So it only works when it's 1 or more. So I know there's always going to be a next here that is not this dummy node here. Then we have to do this walking process, like we did with before we were circular and doubly linked. To add at the end, we had to start at the beginning and go, okay, next, 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 until we got to where we want to be. So we're gonna do this little index. We're gonna say for actually we just do a while loop, I guess. I don't know. Maybe the while loop makes more sense. You could be a for loop too, but we're gonna say, well, the current index is less than the index, because I want to get to the location of where I need to be. So if you want to be at index 0, great. This is what's going to come next. If you want to be at index 1, we need to be looking at index 1 to put ourselves in between the current index 1 and the thing before it. So our current node will just equal the current node.next. Go to the next one here and take current index plus equal 1. Okay. Once we've reached the index we want to be at, right, then I'm going to add myself in between. So we had this add node helper in here, right, that says, okay, what comes next and what comes previous. Perfect, we can do that. So we're going to add a node, given data. Okay, given the data. What comes after this? Well, what comes after this needs to be the current node, and what comes before it needs to be the current node's previous. Right, we need to put ourselves in between them. So let's sketch this out, right? A picture really is worth 1,000 words here. Definitely. Maybe I'll actually click the button and hit on. See if we can get Word to start. Oh, look at that. Dearborn, due to inclement weather, all evening classes are pivoting online or are canceled. See, we beat this here by already being remote. Totally on purpose, right? Excuse me. Oh, I need some more coffee. What is going on here, Word? Just got that emergency alert. So if we had a list here then, right? So we're going to have the start here, right? This is our little dummy node. And then start has a next. And let's put in a 2 here. Its previous is start, and let's maybe put in a 3 over here. These ones point at each other, and then 3 points back to start, and start's previous is the last thing here. Sure, yeah. Yeah, the weather's looking kind of gross out there, so hopefully you folks are staying safe. So if this was our list here then, right, do you want to be the new index 0 or the new index 1? Either one is going to work for us, whichever you want to do. How about we become the new index 1? I think that might work easy. So let's insert the value 7. We're going to say, okay, please put a 7 here at index 1. Sure. So what we're going to do, we're going to start at starts next is the first one. My current index is 0. 0 is less than 1. Current then will move to current's next. So now current is here. This is my current. Okay, indexes match. Our loop is done. Now we're going to say, okay, put a 7 in here. 7, your next is 3. Your previous is what came before 3. Right? And then our add node says, oh, by the way, thing that comes after me, I come after you. And thing that comes after me, I come before you. To hook up those links. And we just break the links here. So this should work. Now, how about performance-wise? What is the performance here? What's the performance of this? And then adding node, does that add our, yep, it increases the number of items, perfect. What's the performance of this? Well, depending on what index is, I have to do that many operations. Right, so if I have 100 items and I want to insert at index 99, I have to go from 0 to 99 to get there. So I'm still O of n here. Right? Now there is a trick. There is a trick here we can do. It's not super helpful. It'll speed it up a little bit, but if you want to, and we're just not going to bother, but fun optimization, you can see if index is closer to the front, closer to 0, 0, or closer to the length of self. If it's closer to 0, do this, right? Start at the beginning at start.next. But if it is closer to the length of self, closer, if it is closer to the length of self, you want to start at start.previous and go backwards. Right? So we could say, oh, hey, if you are the 99th item, I can get there faster by starting at the last thing and going back. Right? Previous. So it's a fun optimization you can do. Previous here. And then there's all sorts of other nonsense you can do if you want to keep indexes or keep references to items at other locations. So there's all sorts of fun math you can do, and that's essentially, when we get down to skip lists, you do some crazy things where you can say, oh, well, let me keep a pointer to a list here and keep a reference to the list here and keep a reference over here. And if I keep a reference every time, like some sort of like logarithmic number of references, right, I'm always going to be within a certain subset of that index. I can get there much faster at the trade-off of using more memory. Again, that sort of optimization really starts to hurt my head. Because you can chunk this up into as many sections as you want. You can say, oh, sure, every 20 items, I'm going to keep a reference. Okay, so this is the 20th item. I know how to get right to the 20th item. Okay, I know how to get right to the 30th item. I know how to get right to the 50th item, right? And that way you can short circuit all of these walks here to get to actually a constant time operation, right? At the trade-off of keeping all of those items in memory. So you'd have to have some sort of collection of here's what the index is, and here's the value. But then that's slow because that has to update every time you add or remove things. So you're never really going to get to fully constant. At best, it's sort of logarithmic, and there's all sorts of fun math there because every time you add or subtract, you need to be adjusting all of those, and you have to look through all of your sequence of those to add and subtract. And again, we'll talk about skip lists later. Let's look at skip lists later. Some really smart people who do really good things have looked at this. So because this is slow, unfortunately, but it was slow for array-based lists too. right? Inserting anywhere near the beginning, array-based lists had to shift everything down. We're slow at the end because we have to count that far out until we know where to insert, right? So that's insert. Now we also had pop, right? So we're going to define pop. And now pop would take an index, but we're going to assume if you don't give me an index, we'll say, how about it's -1? Is that okay? Or maybe none is a better. We'll just say, hey, it's none. And as I can check for none a little easier here. Okay, so if pop is not none, and pop is, so 0 is, if it's not none and pop is less than 0, or pop is, I'm sorry, index. Goodness, why do I keep calling it index? Index is not none, and index is less than 0, or index is greater than or equal to the length of self. So this is our invalid case here then. We're going to raise an index error. Index error. Right, so if you give me one, and it's not this, it's no good here. Right, raise the index error. Okay. If the index is none, if you didn't give me one, we're just going to remove the last item. And oh man, I already had the remove back. Let me just go copy that code here. Right, we had remove back. There we go. We'll go steal that here. So if it is none, then just remove the last one being starts previous. Okay. Otherwise, we need to go get to that location, right? So we have to do this sort of loop here. So we'll say, okay, current index starts here. And again, we could do that sort of fun optimization if we really wanted to, but we're not going to bother. Oops, current index is 0. While the current index is less than index, keep on moving. Once we get to that location, then we can return self.remove node. And what node are we going to remove? We're going to remove the current node. Right? When we remove a node, remember, it just jumps itself in the list. It says, okay, sure. Hey, thing that comes after me, the thing that comes before you is what comes before me. Hey, thing that comes before me, the thing that comes after you is the thing that comes after me. Right? Take the thing before and after me and jump me out. Right? Skip over me, please. And then return the data. I don't actually think we need this current node here. I don't think we need any of that. So this, let's see, we can shorten this up here. So we'll just say node.data here. This is node next, and node next, and node previous, and node previous. We don't even need the data here. We can just return node.data because we still have the node, right? Node still knows about itself. We just took it out of the rest of the list here. Look at that. We made it even shorter. We made it pretty. Okay. All right, I'm feeling bad about this index error here because then all of this stuff is tabbed in. So we want really if not this, then we'll raise that value error. That's not okay? That way, not everything has to be tabbed in that extra line here. It does make life, it's a little prettier here. If you've got something that's going to raise an error, do it first, and then nothing else needs to be tabbed. It kind of keeps things from shifting too far to the side. Okay? And again, I could have done it the other way, like with an or, right? Either one of those is fine. Maybe this is easier to understand here. We'll do that. So we'll say, hey, if it's less than 0 or greater than equal to the length of self, we'll raise that instead of using a not. Because sometimes not this is confusing. So if you can avoid the not, I think this works out better. So you can pop at a given index then. We'll go find that index. Find that node, remove that node. And again, the code is easy because we have this doubly linked circular list going on here. I always have a node here, so I always have a previous, I always have a next. I don't have any code I need to worry about here. And same idea for performance of this one here, right? It's O of, really it's n minus k, right? Where k is the index, n minus the index, essentially, but still O of n, right? On average, O of n. We don't really care what that index is, sure. So pop in the end, yes, constant. anything other than that, once you give it an index, it's essentially going to be linear here, which is, I don't know, how would I say tilde? That's like about O of n here. So I can say with this one here, n minus index, right, which is about O of n. Because on average, right, on our average case here, we don't, if we have to average what index is, half the time it'll be faster, half the time it'll be slower. So on average, it's right in the middle, which is half of n, and we get to throw away coefficients, right? Because funny math, we just get a hand wave, right? Sure, half of n is faster than n, but it's still linear, and that's essentially what we care about. So, being halfway faster if you still have to do a million operations is still pretty slow. Okay, so now I think we do all the things that a list does, right? We can pop, we can insert at a given index. Oh, we can't set, so we need to, for a given item, we need to overwrite the value here. So what is the operation for that here? Hang on one sec. Python, I don't remember what it is. Let me Google it. Override index set. Something like that. So we'll probably get us closer. Get item. Is that get item? Might just be get item. Yeah. Okay, get item. We'll try that. So that must be the get and the set for us here. So that's really cool. So that is the Python operator with those indexes, or with the square braces here. So we can define get item given the, is that item or index? Shoot. Self and index, list is index. Let's try it. We'll try it and see. I don't know. We'll find out if that actually works or not. So to find a given item at an index. So get item, a given index. Is that really? Is that get? Let's try that one more time. See if there's a better autocomplete here. Get, yeah, just item. Okay, probably. I'm going to call that index. We'll see if that is it. So we need to do the walking here, but first we're going to, check to see if it's valid. Now, I have this exact same code more than once here, so let me do this. I'm going to go refactor, and let's introduce a method, or extract method here, for validate index. And now we can just validate index on all of these here with a single call, which is really nice anytime we're doing that, right? So, and, I don't know, this one's a little bit ugly. If it's not none, how about we just validate the index? That's fine. So if it's not none, we'll validate it. If it is none, right, so that's, I guess, else here then. So if you gave it to me, we'll validate it. Otherwise, we give you this. Right? And then if it's not none, we just continue on going here. How about we do this first? So if it is none, then we can just return this. And then we don't need an else, because we're just going to continue on with our code. There we go. I like that. This is even cleaner here. Anytime we have to validate an index, right, we're going to make sure that that is the good number here. Validate index, so validate index. Okay, good. All right, so we validated the index. So now we need to do the walking thing here. Go find the current node. So that's just getting the item. How do I set the item? Yeah, that's not the set. We're going to then, you can return current node dot data. Is that really what it's doing? I don't think it's. I don't think I found a solution here. Here we go. Get item. You need to implement set item. Okay, so get and set. Cool. So to get and set, then we have to do that. You can also do delete. You don't want to do slices. Ugh, slices would be obnoxious. We're not going to bother with slices. So then we can define set item given it's really the index, right? And the value, we'll validate the index. We'll go find all of this here. And then instead of returning the node.data, we're going to say current node.data equals the value. And probably it'd be nice to keep this. So we'll have the old data is the current node.data. We'll set it here, and then we'll one last chance return the old data here for fun. So we can get that back out. So that way you get one last chance to get your value out. All right, but now with all of our lists here, we should be able to make a actual linked list here then is just, oh, we already have it, that's fine. Is going to be our circular doubly linked list here, and we can say linked list dot append. We can append a couple. How about we do for number in range 10. Let's append the number. Right, and then if we want to go change some of these things, let's do for number in range, let's do 10 again here. Number, this will be, how about index? Index in, how about range length of the linked list, right? We'll do our, proper, all these things here. We can take our linked list at the index, and we can assign it the value of, how about index times 2? And we'll double all of them here. Right? And then we should be able to get them back out as well. Right? Just printing out the values by index, because we've overridden those values here. We've overridden the set and the get here, right? So this is going to call the set item here, right? This is going to call the get item, I think. We'll find out. See if it does it for us here. Yeah, so we set them all, and then we get 0, 2, 4, 8, 6, 10, 16, 12, 14, 16, 18. I'm reading too fast here. I think it's too much coffee. So we can do all those things. Okay, and we'll have to test pop in a little while and see if that's all working here. But the performance of this one then, right, for get and set, right, same idea here. O of, n minus the index, but essentially O of n, right? Okay, sets and gets. That's not okay? All right, it is almost 4:45. Wow, that took up our time. So next week then, right, we've got I posted the midterms practice, right? I think I added that for you as a new midterm practice is posted here. Same idea for the midterms. It'll be half the quiz questions and half the these long answer style questions here. Something on recursion, do it recursively and iteratively, something with two-dimensional lists, and something with classes and a unit test. And this is sort of like UML here, right? I'm saying, hey, I'd expect it to be a list here, an int here, a float here. So not exactly quite there, but it's pretty close, okay? So this will open up next week, lab time, which is noon. Right, so we add that midterm here. I gotta rewrite it still, but I'll put it in so at least you can see all the dates and stuff for it. Goodness, come on, load, friend, load. Midterm, for our midterm. There's no time limit. There is available from 22nd at 12 p.m. And then I'll put a due date here. So that'll be a week later. That'll be March 1st. I'd say 10 a.m. If that makes sense. That's the full week then. It's in the middle of break, so I'd rather you get it done and have your break. Don't save it for the Tuesday of break, I suppose. I mean, I guess that's up to you. It's your break, but go with it from there. Okay, so this is open book, open notes, open internet, but not open neighbor. Right? Use your resources, but not other people. Right? And that includes asking other people online or internet stranger. Right? You can't ask internet stranger. but not open neighbor or internet stranger here. We'll force them out of order of operations, right? Okay, so that'll be available for you. You'll have the whole week to work on it, lab time and lecture times. If there's anything else I can do for you, let me know. I'm going to work on getting the rest of the stuff graded. I know I'm a little behind. I apologize. It'll have some points here too in a little while. So, and then in terms of quizzes, right, the rest of the quizzes here, we're going to have, you've got all in here. I'm going to post the last one on linked lists for you too. Hopefully you'll get that one done before you take the quiz. If you, I mean, I'll set the due date for Thursday if you want to wait, and I'll get those graded as soon as I see them come in, if I can help it here. I got to post the chapter, is that chapter 6? Why can't I even remember now? I think that was linked lists. So the thing we were just doing, I didn't remember the chapter number. Let's see here. Chapter 6. Yep. Oh no, chapter 7. Did we not do one on 6? 6 and 7. Oh my goodness, really? Did we miss that one? Two, four, five. Yeah, okay, so we need 6 and 7. I'm sorry, we'll do 6 and 7 then. 6 and 7. Because you need enough of a bank here for 6 and 7. Otherwise, it's really boring to just get those same questions over and over again, okay? So I'll post those ones for you. I really thought I did 6, because it was like just 5 questions, wasn't it? Am I going crazy now? Maybe I'm going crazy. Oh, no, okay, no. The other one was short. I see it there. I was looking at points, not questions. All right, folks, will you take care? Let me know if there's anything I can do for you. And then for fun, we should see if anyone's around streaming soon. Let me put on this ending here, because otherwise my browser just locks up trying to see what else is on. We'll send it right over to someone else who's doing some fun stuff with code, maybe. And just part of the fun of Twitch. You go say hi to somebody, meet a friend. Let's see who's around. Oh, wow, there's around. Go check them out. I haven't been there in a while. Does lots of really cool low-level stuff with tech. You'll have a lot of fun there. We'll head over there and say hi. And you folks take care. All right. I will see you in 3 weeks then, I think. Take care, everybody.